So that's what I mean. But so now you've seen the error detection and correction capability of a code. Now it's possible to do this in a more systematic fashion. I told you what we mean by error detection capability and the error correction capability. But we can make this a little more rigorous in a slightly more elegant fashion. And the way to do it is using this notion of a Hamming distance. Right now we're assuming that the only kind of errors that can be made are substitution errors. Right? You pick certain number of locations, and in those locations you change the symbols. Okay? So I'll denote the number of changes made by a special symbol. So given any two sequences, xn and yn, both of length n, I'll denote dh of xn, yn as the number of locations in which the two sequences differ. So think of it in the following way: xn is the transmitted sequence. Some of these symbols are changed to give the received sequence, which is yn. And dh of xn, yn is exactly the number of locations which have been changed. So this quantity is what is called the Hamming distance between xn and yn, right? And I'll introduce one more notation. So wt subscript h of xn, which is basically the Hamming distance between the all zero sequence and the given sequence x. Right? That's what is called the Hamming weight of a given sequence. Okay, so just quick example. So what is the Hamming distance between these two? So these two differ in this location, this location, this location, and this location. So therefore the Hamming distance n is equal to 4. What are the Hamming weights of xn and yn? So the Hamming weight of this sequence is 3 because it has exactly 3 ones, and the Hamming weight of this is 1 because it has a 1 1. Now n, let me call this Zn. So this is my Zn. So what is the Hamming distance between yn and Zn? Three. They differ in exactly these locations, this one, this one. So the Hamming distance is 3. What is the Hamming weight of Zn? 4, right? Because there are 4 non-zero elements. So the Hamming distance and Hamming weight can be defined for any alphabet, but of course for the Hamming weight to make sense, there should be a special 0 symbol in the alphabet. But irrespective of what the alphabet is, even whether it contains a 0 or not, you can always define the Hamming distance. But of course the Hamming distance is defined only for sequences, pairs of sequences of the same length. Okay, it doesn't make sense if the two lengths are different. And this particularly makes sense when the kind of errors that we are considering are substitution errors. Actually, some locations have. Because a nice feature about substitution errors is that you can kind of think of this as an additive channel, right? Okay, so let's take the binary case just for simplicity, although you can do this for any given channel. So suppose that this is the transmitted sequence, okay? And maybe 3 locations are changed, 0, 0. this location are changed. Can I write yn as xn plus some error vector? What would the error vector be in this particular case? It would be 0, 1, 0, 1. So whichever locations are changed, put a 1 in that particular location, and the others you put a 0. So now suppose I give you any pair of xn and yn, both binary. Okay. Can I always write yn as xn plus something? I can always do that, right? But remember that this plus symbol that I have is basically the element wise XOR operation. And what is Wn equal to? How do you, so if I give you a particular xn and yn, how will you exactly use the? So it's basically just the XOR of xn and yn. And as you pointed out, it's 1 in the location where xn and yn differ. Okay, so now using this point, is there some relationship between the Hamming distance between xn and yn and the Hamming weight of wn? They're going to be the same. So the Hamming weight of this error sequence is basically equal to the Hamming distance between xn. So this substitution error model can be thought of in the following way. So you're transmitting a sequence xn, and you receive a sequence yn, and there's an error sequence which is added to it. But how is this error sequence chosen? We can model this as an adversarial channel, right, wherein the adversary can see the entire xn and choose a wn such that the Hamming weight is less than or equal to some quantity. Okay, let me use a different L. So this is a channel which introduces at most L errors in the transmission. So this is basically what I refer to as the adversarial . So if you want to design a code for such a system, you want to ensure that for every error sequence which is added, as long as the error sequence has weight less than or equal to L, you should be able to correct the. And the way of thinking, so basically a code is L error correctable if for every error vector of weight L that is added to the transmission, there is a mechanism which allows you to recover the transmitted code word from the received sequence. And similarly, you can also redefine the error detection capability of a code in the following way. So as long as an error of weight less than or equal to L is added to the transmit to any other code word, this does not result in any other code. This is one way to define the error correction capability of a code. Similarly, we say that a code, so this holds for all detectable if plus wn is not in the code book. If I add a wn, then it does not result in any other code word as long as weight of wn is less than or equal to. So what can you say about the Hamming distance between every pair of code words in a code which is L error detectable? So suppose I tell you, I give you a code and I say that this can detect L errors. Okay, that's one parameter, the error detection capability of a code. And there's another parameter that I'm interested in, which is the minimum distance, the minimum Hamming distance between every pair of code. Why? So basically, if the error detection capability is less than the Hamming distance, then that's impossible, right? Because there is some error vector of weight. If the minimum distance is less than L or even equal to L, then it is possible to go from one code word to another code word using just L substitute. Therefore, the Hamming distance, the minimum distance between every pair of code words, should be at least L. But on the other hand, suppose that the minimum distance between every pair of code words is say L minus 2. Then sorry, is say L plus 2. Can it detect L errors? So I define the minimum distance of a code as just the minimum Hamming distance among all possible pairs of code. Okay. So this point is clear. The definition of the minimum distance is clear. Okay. So now suppose C can detect L errors. Clearly, L should be cannot be any larger than D. Should be strictly less than D. Otherwise, what can happen? So there should be some error vector, right? So let's take the following example. So what is the minimum distance in this for this particular code? Uh, 3. What is the distance between the first two? 3. The distance between the second and the third? 4. The distance between the first and the third? 3. Yes, fine. So now the minimum distance is 3. Correct. Can this code detect 2 errors? It can. Can it detect 3 errors? Okay, so let's ponder on that point a bit. So 3 errors are not detected. Not all 3 errors can be detected. So it's possible that some error vectors of Hamming weight 3 can be detected. It's always possible. What we're interested in is if all error patterns of length at most 3 can be detected or not. Okay, so is there an error pattern of length 3, of basically of weight 3, which cannot be detected? Huh? So let me call this C1, C2, and C3. So yeah, the first code word. Okay. Zero. Okay. Yeah, so basically what we're trying to say is that C1 plus this vector gives you C3, which means that there is an error vector of weight 3, which confuses you between C1 and C3. So C1 plus this error vector gives you C3. So this error vector cannot be detected. So therefore there is at least one error vector of weight 3 which cannot be detected. So it cannot detect all combinations of 3 errors. Okay. So now so therefore L should be strictly less than the minimum distance. What if L is actually less than the minimum distance? Is it possible to detect all such errors in that case? So in this particular example, you know that the minimum distance is 3, right? Can it detect all combinations of two errors? Yep. Yeah. It's not possible to get any other code. Otherwise, that would violate the definition of the Hamming of the minimum distance. So, so as long as the number of errors is strictly less than the minimum distance, you will always be able to detect it. Or exactly the same code word has been transmitted, no errors. So that is good. Fine. The minimum what? The minimum Hamming weight of the error vector. So in this case, okay, so in this for this particular code, what is the minimum weight of the code? Y2. What about C1? 1, right? So the minimum weight among all possible code words is 1. So the minimum weight of this code is 1, but the minimum distance is 3. So I think what you're pointing out to is, are the minimum weight of a code and the minimum distance the same? In general, they are not. But as we'll see later, for linear codes, the minimum weight is equal to the minimum distance. Okay, so that's the error. That's the connection between the error detection capability and the minimum distance. So if the minimum distance is dmin, then any error pattern of at most dmin minus 1 can always be corrected, can always be detected. Now, what can you say about the error correction capability? So in this, for this particular code, how many errors do you think it can correct? You should remember, you should be able to recover the transmitted code word exactly. You're saying that every collection, every error pattern of 2, of weight 2 can be corrected. So suppose I have C1 plus 0 1 0 1 0. Okay. So this gives me what? Gives me 0 0 0 0 1. Sorry. Zero. Okay. Now, what if I take C2 plus say 0, take C3 plus 0 0. So now do you claim that every error pattern of weight 2 can be corrected? So suppose that you received 0 0 0 1 0. Okay. What would you declare as the transmitted code? Potentially C3, right? But then there is an error vector of length 2 of weight 2, which sort of gives you which transforms C1 to this particular sequence. So not every error pattern of weight 2 can be corrected. There exists at least one error pattern of weight 2 which cannot be corrected. Okay, so now let's so 2 is not correctable. Okay, so let's think about it. Okay? What do I mean when I say that it is 2 error correctable? It means that irrespective of which 2 locations I pick, 2 or less than 2 locations I pick, I should be able to recover the transmitted code word from the received sequence as long as at most 2 locations have been changed. Correct? So in this particular case, if I add C1 plus 01010, I get this particular received sequence. Correct? If I add C, so now if suppose that I received this particular sequence, I know that C1 plus this is equal to this sequence, but C3 plus this vector also gives the same sequence. Now at the decoder, what would I declare? It makes more sense to declare C3 rather than C1 because the Hamming distance is smaller. So therefore, there is some error pattern of weight 2 which cannot be corrected. You all agree? Okay. So now, can all error patterns of weight 1 be corrected? Why do you say that? Okay. The what? Yeah. Correct. Correct. Hmm? Okay, I mean you're along the right track, but you need to state that a little more precisely. So the right quantity to look at is, so you know that the minimum distance of the code is 3. Okay, so for every code word that is transmitted, right? What can you say about the distance between n and yn? No, so every time I'm introducing one error, right? I can introduce at most one error, right? So what can you say about the distance? Is less than or equal to 1, right? Okay. So now what is the distance? So what will your decoder be? What kind of a decoder are you assuming? Because whenever I'm saying error correction capability, it implicitly requires you to define a decoder. You could define a bad decoder for which it doesn't correct anything. So how would your decoder operate? You already have it here, right? So using this intuition. we'll find the code. Okay. Okay. So what how exactly does the decoder operate? You do you receive a sequence. Given the received sequence, okay. If it does not match one okay. It should match it should flip in such a way that match the code. So another way probably of restating this is you find the distance to every code word in the code book, find out which minimizes the distance to the received. In some sense, which code word is closest to what has been received, and you just declare that as the transmitter. Right? That's one way of doing it. That's essentially what you explained. So this is a minimum Hamming distance decoder. You compute the Hamming distance between the received sequence and every code word. And you choose the scene that minimizes this. So in other words, your estimate is basically min is one way of defining the decoder. Right? Okay, very good. So now I'm telling you that the Hamming distance between the true transmitted code word and the received sequence is at most 1, because only those kinds of errors are permissible in this channel. And the minimum distance of the code is 3. Okay. So now what will be the minimum distance between the received sequence and all other code words? You sure? Only 1? Okay. So this is what we're given, right? We're given that the minimum distance is 3, and the distance between xn and yn is 1. So that's basically this Hamming distance between the received sequence and the true code word. Now I'm in trouble if there is some other code word for which the distance between yn and the cn is at most 1. As long as it is strictly greater than 1, I'm happy. There won't be any error. So what can you say about the distance between yn and any other code word? Why? No, I know, but that's what I want to show, that right, whether I can decode it properly. Okay, one error was made, I agree, but then why are you claiming that the distance between the received sequence and every other code word is 2, at least 2. Okay, so you're basically relying on this particular example. So let's try to make this a little more formal. And the interesting observation here is that the Hamming distance, as I have defined it, I use the term distance. It is actually a true distance, just like the Euclidean distance, because it satisfies the following properties. It is what is called a metric in mathematics. So any function which takes two inputs, two sequences as inputs, and outputs a real number is called a metric if the following properties hold. So let's think about our Euclidean distance, right? What is the Euclidean? What can you say about the Euclidean distance? It's always non-negative, right? It's greater than or equal to 0. It is equal to 0 only if the 2 points are coincide, right? So that's point number 1, and that is what we want any distance function to be, right? So if you say that I'm giving you 2 points and I'm talking about some distance, obviously it should be greater than or equal to 0, and it should be equal to 0 only if and only if the 2 points are exactly the same. It should be symmetric, right? The distance between point A to point B is the same as the distance from point B to point A. That's symmetry. The third point, which is really what makes it a metric, for which we call it a metric, is that it satisfies triangle inequality. So that's one intuition or property from Euclidean distance that we'll borrow to extend it to a general metric. Right? So if I take any 3 points, right, I take any 3 points. If I look at the distance from point A to point B and add the distance from point B to point C, then this should be greater than or equal to the distance, to the straight line distance from point A to point. So this is the triangle inequality. And a function is said to be a metric if and only if it satisfies all these 3 properties. It satisfies property number 1, it is symmetric, and it satisfies the triangle inequality. So now let's look at the Hamming distance. Is it a metric or not? Does it satisfy the first property? So the Hamming distance between every pair of sequences is greater than or equal to 0. It's some positive, non-negative integer, right? And it's equal to 0 only if the 2 sequences are the same, exactly the same. So it satisfies property 1. What about property 2? Yeah, it is symmetric. The Hamming distance between x and y is the same as the Hamming distance between y and x, because all you're counting is the number of locations in which they are different. Right? It doesn't depend on which order you present the 2 sequences in. Okay, but now the third part is slightly more interesting. So does it satisfy triangle inequality? Okay, why do you say that? I want a general proof. Basically, if I give you 3 sequences, same length, then the number of locations in which xn and zn differ is always going to be less than or equal to the number of locations in which xn and yn differ, plus the number of locations in which yn and zn differ. That's the statement that we're trying to prove. Now, the simpler way of proving this is by looking at the Hamming distance in a slightly different way. There's a number of locations in which the two sequences differ, but another way of thinking about it is the following way. So if I give you two sequences xn and yn, the Hamming distance is exactly the number of locations which need to be changed to go from xn to yn. The number of locations which need to be changed. Now, can you use this to say why this particular statement is true?
From xn to something, something. From there, either we can to be yn only, yn at y, or at least make one more change.
Can you think about it and get more precise? So remember that the Hamming distance is not just any number of changes that you need to make. It is the minimum number of changes that you need to make to go from xn to yn. Okay, because there are a number of different things you can do to go from xn and y, right? Yes. So suppose I want to go from xn to zn. One way to do it is, make the minimum number of changes required, go from xn to zn. Basically, you flip exactly those locations in which xn and zn differ. The number of flips that you need to make is exactly equal to the Hamming distance between xn and zn. Now, there's another way of going from xn to zn. You make two sequence of changes, a sequence of two changes. So one is you make a sequence of changes which takes you from xn to yn, and you make another sequence of changes which takes you from yn to zn. Okay? The minimum number of changes you need to make to go from xn to yn is what? Hamming distance between xn and the minimum number of changes that you need to make to go from yn to zn is dh of y and zn. Right? But by definition, the Hamming distance between xn and zn is the minimum number of changes to go from xn to zn. Right? And another way of making changes to go from xn to zn is this route via yn. So obviously, by definition, the number of changes to go from here to here directly should be less than or equal to the number of changes you need to make to go via yn. Correct? But what is the number of changes here in this route? in this particular route? Exactly, that's precisely the right hand side. Right? On this direct route gives you the quantity on the left hand side. So obviously this should be less than or equal to dh of xn yn plus dh of yn zn. Okay, so therefore the Hamming distance satisfies the triangle inequality. So now let's go back to the original question we had. Right, so I give you a code with minimum distance 3. So every pair of code words is separated by a Hamming distance of at least 3. And I'm saying that the error vector can only introduce errors which result in dh of x and yn to be less than or equal to 1. So now what can you say about cn yn or any other code word? So by this I mean the code book with the true code word, the transmitted code word removed from. And why? Okay, how exactly are you using it? Okay, so dh of xn, so you know that this is greater than or equal. Okay, good. Okay. N plus Hamming distance between n. You know that this is at most, okay, or in other words, h n is greater than or equal to 3 minus the Hamming distance between xn and yn. But you know that this quantity can be at most 1. Therefore, this is greater than or equal to 1. So the Hamming distance between the received sequence and the transmitted sequence and any other code word, it must be at least 2. So the minimum distance decoder is always guaranteed to output the correct answer as long as the number of errors is at most 1. Okay, so now can we generalize this? Suppose I tell you that the minimum distance is dmin. Every pair of code words is separated by a Hamming distance of at least dmin. Dmin minus 2. Suppose dmin is 100. Are you saying that you can correct 98 errors? So the way to think about it is geometrically, right? You think about it in, of course, I'm going to draw a picture. It's of course using Euclidean geometry, which is not valid, but it's still, some of the principles still carry over. So I give you a bunch of points, right? And I'm telling you that the minimum distance between every point, every pair of points, is at least dmin. Okay. Now what is happening? The channel is introducing errors, right? Or in other words, it's perturbing this. So from this, you go to some point within a distance something, so let's say L, right? So it could basically lie anywhere in this ball of radius L. And so the received sequence, as long as at most L errors are made, the received sequence will lie within a ball of radius L around the transmitted code. Right? And when can we say that we can always correct L errors? Now, for every code word, there is going to be the ball of received sequences, correct? Conditioned on that particular transmitted, on that code word being set, correct? So now what happens if any two balls overlap? Can you correct the errors? No, right? So no, those error patterns can't be corrected. So L errors can be corrected only if these balls of radius L never intersect with each other. So now you know that the minimum distance between every pair of points is some quantity, d min. So now what do you think should be the relationship between L and d min, roughly? Yes? So I'm giving you a bunch of points and I'm drawing balls around them of radius something, L. Okay? And I'm telling you the minimum distance between every pair of points is d min. So how large can L be such that no two balls intersect? Roughly d min by 2. Do you all agree? So if it's any larger than d min by 2, then there would be some pair of balls which intersect. I'm not sure that it's exactly d min by 2, but if it is larger than d min by 2, then certainly they will intersect. Do you agree with that? Yes, no? So if L is greater than d min by 2, right, there is some way of, so let's take 2 points. Okay, so you know that there is at least one, there exists some xn and cn such that Hamming distance between xn and cn is exactly equal to d min, because by definition there should be at least one pair which are separated by d min apart, correct? So let me take xn plus what can I say about the weight? Yeah, so this is exactly d min. Now I'm allowed to make whatever L greater than d min by 2 errors, right? So now strictly greater than d min by 2. Now if I take an en tilde, so I basically take this en and I pick some L locations out of any L locations which are non-zero. Pick any L non-zero locations from this particular en and add it to xn. Okay. Then the distance between, let me call this yn. The distance between yn and xn is what? It is L. I'm picking L locations, basically L locations which are 1 in en. But what can I say about the distance between yn and cn? Will it be less than L or greater than L? It will be less than L. So the sort of geometric way of thinking about it is the following. So I'm giving you 2 points, correct? This is my n, and Cn, the distance between these two is dmin, correct? What I'm choosing is basically an error vector which is along xn and Cn, right? From which takes xn to Cn. So I choose an error vector which takes me just beyond the midpoint. Okay, because I'm allowed to make those many errors. I'm allowed to make more than dmin by 2 errors, correct? So if I pick an error vector along this particular direction, then the decoder will output Cn. A minimum distance decoder will output Cn when the actual transmitted code word is actually. So how many errors can you correct? It should be strictly less than dmin by 2. Okay. Any code can correct has to be strictly less than dmin by 2. So the error correction capability is strictly less than the minimum distance divided by 2, strictly less than, equal to minimum distance. In fact, you can make this slightly more formal. So given any code which has a minimum distance which is at least 2, satisfies the following. So if d is odd, then it can correct exactly d minus 1 by 2 errors. Because d is, if d is odd, then it can correct strictly less than d by 2 errors, which is basically d minus 1 by 2, smallest integer which is less than d by 2. Sorry, the largest integer less than d. If d is even, then it can basically correct d by 2 minus 1 error. It can, if you think about it, it can detect d minus 1 errors, as I guess we discussed earlier. And also, the code can correct d minus 1 erasures. Can you tell me why? So the first 3 points are hopefully clear. What about point 4? The code can correct d minus 1 erasures. So if I erase any d minus 1 locations, I'll still be able to recover the original transmitted code. Okay. Okay, but do you think that's a good strategy? Okay, so suppose you had this erasure channel, right? So the way to think about it is how is your decoder going to operate? What is the simplest decoder you can think of? So remember that the erasure channel does not introduce errors, right? So some locations get erased, but bits never get flipped. So what would be what decoder would you propose? What is that? Okay, but remember it's not probabilistic. Some set of L locations are erased. So the minimum what is the minimum distance for this code? minimum distance is 3. Okay. So now suppose I give you, let's say 0, 1, erasure, 1. What would you decode it as? 0, 1, 0, 0. So now if I give you, let's say 1, erasure, 0, what would you decode it as? C2, the second code. Okay, so now what are you doing? Your mind. Okay, but this is simpler way to think about the erasure channel. You're minimizing the Hamming distance. Okay, that's not exactly what. You're not doing actually any Hamming distance in your head. What you're basically doing is you look at the unerased locations and find out which code words match in the unerased location. All that you're doing right now. And in fact, if you think about it, that's all that you can do. This particular decoder is actually optimal. If there are two code words which match in the erased, basically match in the unerased locations, two different code words which match in the unerased locations, then there's no way of distinguishing between the two. You can design a decoder, but always which outputs some unique code word, but not guaranteed to be optimal. Basically, if there is at most one code word which matches in the unerased locations, then you always declare that as the code. Right? That is going to be the decode. Okay. So now suppose I make at most d-1 erasures. Right? Can this result in another? Can there be a conflict between two code words? So basically, I take sequence at a code word and I erase d-1 locations. Okay, so I'm basically revealing the remaining locations. So in the remaining locations, so I pick any d locations, sorry, any d-1 locations, I erase them. In the remaining locations, can two code words be the same? So take any pair of sequence, C1n and C2n. What is given? You are given that the distance between C1n and n is whatever d. It's greater than or equal to d. Okay. So basically, I'm taking C1n n. Okay. And I'm telling you that they differ in at least d locations. Now, what happens when it is erased? So you can think about it in the following way. So some locations are completely removed, right? You basically remove a chunk. And what does the decoder do? It looks at the remaining locations and sees if there's a difference between them or not. So there's a confusion between these two sequences only if they match in all the unraised locations. But what do I know? I know that suppose that L locations are erased. So basically L of these, they remove a chunk of size L. Now in the remaining locations, how many differences can there be? So in general, right? So I'm telling you that at least D locations are different, and I'm basically removing a chunk. Maybe I remove the first L location. So all you will see is the remaining n minus L length code words. So what can you say about the Hamming distance in these locations? It should be at least D minus L, correct? So suppose I get C1 tilde erasing L locations. Then the distance between 1 tilde should be at least D minus L. Right? You all agree? Right. So if the number of erasures is strictly less than D, then you can always recover the transmitted sequence, right? Because there is going to be exactly one sequence, a transmitted sequence, which differs in no locations at all. And for all other code words, there's going to be at least a 1-bit difference in the unerased location. So any erasure pattern L less than or equal to D minus erasures can be correct. Right? Okay. So before we wrap up, here are a couple of examples of codes. Right? So we've seen some toy examples in between, but here are some general, very simple codes, which are also used in practice. So one is the parity code. So you have a sequence of k bits. The code word is basically the same sequence of k bits appended with the parity, which is the XOR of all the k bits. So it's so what are n and d? Sorry, n and k in this particular case. M maybe. It is k plus 1. How many messages are there? Are you sure there are only k messages? 2 to the power k. So it is a k plus 1, 2 to the power k code. So for this, I want you to compute the minimum distance of code and what is the error detection and correction capability. So I leave that as a homework. Right? And the second is the repetition code. So basically, if I have a message bit M1, then I need another parameter, which let me call it R. So R is the number of repetitions. What are n and k in this case? Assuming that these are binary, of course. Yep, R. r comma 2. Again, for this, what is the minimum distance, and how many erasures can it correct? And one more thing for the next class, you just revise whatever you studied in linear algebra. What is a vector space? What is a subspace? What is a field? So on. Have you all seen a field before? The notion of a field? Okay, so we'll meet on Monday. Oh, Monday is a holiday. So next Thursday.